What up, everybody? Today we're going to be doing a big constant velocity question. This came from a test a couple years ago and has a little bit of everything. And so just take a look at it, see if you can do it, pause the video, and then come back and we'll go over this together. Alright, and so this has a little bit of everything. It has a scenario where you draw the motion on a position time graph. There's a position, time and position data table. And then you have to find velocity, you have to find displacement, distance, and you also have to convert the position time graph to a velocity time graph. Alright, if you have any trouble during this video and you want to know more, we'll have links throughout the video that you can click on and see, get some help on that specific topic. Alright, so let's begin. Reading the story, it says that Mary started at Scott's house and rode her skateboard with a constant velocity until she reached the lake 3 hours later. Alright, so she started at Scott's house, which is 30. Alright, and so time and position data table is there. Her position starting point is going to be right here on the position time graph. She reached the lake 3 hours later. The lake was at 90. So 3 hours later, she's at 90. I'll put another dot on the position versus time graph. At the lake, she stayed and ate lunch. After 3 hours, she rode her skateboard with a constant velocity. So 3 hours, she's just going to stay there, which will put her from 3 hours to 6. She'll be at 90. And you can see that in between here, right, that should be a flat line. Right, I made it a little curved. She's not going to move. She's just going to stay at 90 because she's there at the lake eating lunch. After 3 hours, she rode her skateboard home with a constant velocity. She reached her house 6 hours after leaving the lake. Okay, so she left the lake at 6 hours and 6 more hours till she got home. Her home's at 0, so we're going to draw the next dot right here. Alright, and so it said constant velocity, and so there's no speeding up or slowing down, so you can connect these lines with a straight line that goes from one to another, and that line should have the same slope throughout because it was constant velocity. You can also do that to her initial motion, and there you have her position time graph. Okay, we also got the information that she made it home at 12 hours, so there we're going to put a 0. Now, it's going to take a little thinking to fill out the rest of this, but she's moving at a constant velocity, so you'd have to count by the same interval. Right? So some number that if you add it here and here, you get 90 by the time you get 3. And so in that case, our number is 20. 30 plus 20 is 50. 50 plus 20 is 70. And you see 70 plus 20 is 90. Alright, so for it to go this far in 3 hours, it went 60 miles in 3 hours. 60 divided by 3 is 20, so that makes sense. Now it's going to go 90 miles in, and it's go down, the position goes down 90 miles in 6 hours. 90 divided by 6 is 15. Alright, so it's going to go down by 15. 75, 60, 45, 30, and 15. Alright, so there's our time and position table. Now let's come over here and start looking at the velocity. Now the velocity is the slope of a position versus time graph, and it even tells us that right there in case we forgot. And so the slope here at 1 hour, you're right here. You're on this line. This line has the same slope, the same velocity throughout. So you can use any 2 points. Just let's use the stop and ending points. It goes up 60, right? Because I know it goes up to 90, but it starts at 30. And so 30 up to 90 is only an increase of 60. Then it goes up, and then across it goes 3 hours. So our rise over run would be 60 divided by 3, which would equal 20 miles per hour. Alright, next 4 hours, we come up here to the flat line. It's not going up at all. Right, so that's going to be 0 miles per hour. Then at 8, it's going down, and so we're going to find the rise over run. And the rise, it goes down from 90 to 0, so a loss of 90 meters of position. And then from 6 to 12 is 6 hours. If you divide those, you get rise over run, which would be minus 90 over 6 equals minus 15. All right? And we must be on the same track, because look what's happened here. At 1 hour here, it was increasing by 20. And what did we find from the slope? 20 miles an hour. At 4 hours, it was not increasing at all. The position was not, just staying at 90. And at 4 hours here, we found that it was 0 miles an hour. And at 8 hours, you can see it was going down by 15. Velocity was minus 15. So not really any doubt there. It's good to check it that way, but it definitely worked out. Now let's come over here and look at the velocity time graph. All right, and see what we're supposed to do. So we had a velocity of 20. How long did that last? We can see it changes here. So at 1, the velocity is 20. The slope doesn't change, neither does the velocity until you get to 3. So we're going to take a line at 20, and that line is going to be flat until we get to 3 hours right here. Then we stop that line, because here at 3 hours it changes its velocity to 0, and that 0 lasts until you get to 6 hours. So between 3 and 6, I'm just going to kind of rub my pen there so you can see that there's a line, because it's a flat line at 0. It's kind of hard to see on some of these graphs. And then at 8 hours, you can see at 6 hours it changes into this slope, and we just found that the slope of that line was minus 15, and that lasts all the way from 6 hours to 12 hours. So there's minus 15, it goes from 6 to 12. All right, so there's our velocity graph. Sometimes when there's a jump like this, people draw a dotted line so you can kind of see it better. All right, so that's how we go from the position graph to the velocity time graph. Now we have some questions about, this one's about momentum. All right, so on the position time graph, circle the part where Mary's momentum was the greatest. Well, assuming Mary didn't really gain or lose any weight during this day, momentum is equal to mass, which would have stayed the same, times velocity. And so the greatest momentum is going to happen when she had the greatest velocity, which was right here, the steepest line, because she was going 20 miles per hour at that point. What was Mary's displacement when she was eating lunch? All right, and the question's asking, like, from the time she got there to start eating lunch to the time she's done. Obviously, she didn't move that during that time, but during that time, I think it's asking how close she was to where she started. So displacement would be final position minus initial position. All right, while she's eating lunch, her position is 90. Minus initial position was 30. Giving her a displacement of 60 miles. Next question, what was Mary's displacement when she returned home? And she returned home, her final position was 0. Her initial position is still 30. So minus 30 miles per hour. Oh no, it's not miles per hour, it's miles, I'm sorry. Displacement when she got home was minus 30. Looking at this motion, she's to the left of where she started. She started here. So you go back 30 meters, the 30 miles to get to where she started. Okay, next question. What was Mary's total distance traveled by the time she returned home? All right, and so for distance, you have to keep track of how far she went this direction and back. So she went from, remember, Scott's house to the lake. So that's 60 miles, right, from 30 miles to 90 miles. And then after that, she went from the lake back to her house, which was 90 miles. And so the total distance she traveled was 60 plus 90 equals 150. You could have found that out by looking at the graph, because you see this goes up from 30 to 90, which is an increase of 60. And this goes down from 90 down to 0. That's an increase of 90 for distance. So you just add those together, get 150 miles. Finally, what was Mary's displacement at 10 hours? Defend your answer. So at 10 hours, she was right here, and that's actually right at 30 miles. And so her final position is 30, and then her starting position was also 30 miles. So if you subtract those, you get 0 miles. Right, so her displacement at 10 hours, she was back where she started. So that's when she passed, on the way home, she passed Scott's house. Right, so that's why the displacement was 0, because she started there, and now she's just passing that point. But her final displacement was going to be minus 30, as we found here. Okay, hopefully that helps. Click on the links to any other videos if you think you need help with a specific topic, and I'll see you all in another video.